Hello, everyone. My name is Aydogan, and I'm Associate Professor at Spitzer School of Architecture. I would like to thank Anna Dyson, first of all, to invite me for this presentation and panel discussion. And she was also my PhD advisor when I was doing my doctorate at Rensselaer Polytechnic Institute. And she gave me the motivation and excitement about this project, and I keep doing it. So she's very good at that. Thank you, Anna. So today's topic is emerging plant systems for improving air quality and reducing energy consumption. So when we look at indoor environments, there are three major problems that we are facing. The first one is air quality, indoor air quality, and the second one is the energy. And the third one, who everybody is neglecting a little bit, is the human health and well-being. So, and ASHRAE is struggling between the two, especially air quality and energy, to maintain acceptable levels in indoor environments. So to maintain indoor air quality, ventilation is increased, therefore energy consumption increased. So when they reduce the energy consumption, so basically they seal the buildings more, and then indoor air quality problems rises, which are directly related to the human health and well-being. So we are saying that as a project, how plant-based systems can be a solution of all the three problems listed above. So to do that, I would like to show kind of a building section. And I want to kind of start with a question. How can plant-based filtration system remediate indoor air quality while reducing the overall energy of the building HVAC systems? As we know, buildings HVACs are required with the code to take fresh air from outside. And they filter this fresh air and supply to the indoor environments. But when they're getting this fresh air, they either heat or cool the external air to satisfy the indoor requirements. And the air which is inside get polluted from the people, from the materials, and return back to the HVAC. Some of them kind of sent out and some of them recycled back. So as an idea, we are saying why we are not integrated plant systems inside which can filter this air, and you can use these systems as a return air filters and connect to HVAC, therefore you are reducing the outdoor intake, therefore you are minimizing the energy consumption by not heating or cooling the external air intake. So this slide is showing basically two different filters. The one on the left is synthetic filters, where you can find an HVAC system. And the one on the right is the organic filter, where you can find in our plant-based systems. So the one on the left needs to be replaced in every 3 to 6 months, but the one on the right have a capacity with the plants and their microorganisms to digest these toxins and turn them to their nutrients. Therefore, the media is recycling itself. To make a general kind of an idea, this project is multiscalar project. And we are mostly working right now in the building scale, room scale, and a micro scale, but we have also collaborators working with us in a nanoscale and global scale. So one of the most important points about this research is kind of a lab-based experiments. So starting from kind of plants and their growing media, and where they're standing and their living conditions, their kind of air quality performance, and a bunch of different parameters are getting into these lab scale experiments. And when we are talking about research and lab scale experiments, this is very interesting kind of a grant we got from US Army, which our goal was to develop a biocompatible absorbance for using self-generated botanically based air purification system. So our goal was the same in this project, where I collaborated with a chemical engineering department in our school. So basically we were trying to create filters that can be used in a warfare zones. So for this, the building kind of a section change, we would like to filter outside air, which is toxic with sarin gas, basically, what the goal was. And we're also trying to recycle the indoor gases, which is created in the warfare shelters. So for this project, we take as a base, as kind of a small kind of a container, which is 8 feet by 20 feet, and all the kind of research is continue on that. And we were looking for plants, we were looking for growing media, and we were looking for different chemicals which can be tethered to this growing media, which are targeted to the specific sarin gas capture. And the ones you see on the bottom, first one is the growing media. We are kind of granulating the media, therefore absorbance and aggregate can equally distribute on the vertical surfaces. Therefore, we will have efficient filtration in all the surface part. And on the second part, you see how plants are responding on that environment. And on the right part, you see the lab scale kind of experiments to show the plant species and their reaction to this growing media. And I don't want to go so much deep in this lab scale kind of experiments, but I want to start with kind of an idea also how to make this lab scale with a building scale kind of ideas and make the connection between them. So this is the first model that we start with the idea. How we should design a system, how we should design a system which can create natural channels on the back of the cassettes to allow the air pass. Therefore, we can reduce the space from 1 foot to 6 inches, which is a huge kind of achievement for indoor spaces in architecture or in engineering applications. So, and we would like to create these channels by creating kind of tilted surfaces on the back of that variation. And we were looking for dynamic iterations. Therefore, we were using equilateral triangles, which can support itself vertically. So since this started with the Army, we were also thinking fabrication systems, how we can fabricate it, and we can send this as a kind of flat sheets, and it can also assembled on the site when it arrives to the location. Therefore, the fabrication system has to be easy to assemble, and then we kind of use it in a way, kind of 3D print the sheets and then fold them and attach them in the joints. So, but again, every kind of research and design is running either with lab scale experiments or simulation analysis. And to achieve this kind of results, we were looking maybe 120 different variations. The design variations that starting from the lid to the corner, to the media, to the extrusion depth, and so on. And what we find out is the flat 2 inches lid with the sharp edges are giving us the best airflow results to minimize the pressure drops in the system to be generated. And of course, we are kind of, every time we design, we would like to fabricate. And this is kind of images that you're looking in the fabrication process. You can see how this system is watered with the dripping system on the left top, and how the mesh is created to hold the plants, how the back structure is created when one type of the panel system is assembled, and how LEDs are attached to the structures to give enough light to the plants, and when we start putting them together. And this is how we end the structure. So on the left, you see kind of a panel prototype, which is one-sided, but there's also a second side, which is not showing on the picture. But also what needs to be clear, this system is a modular system. Therefore, you do not need to shut off all the components. So you can work modularly. If there's a problem, you can take the cassette out and put another one and work on that direction. And we want to take this research a little bit further and say, how about we can give a little bit dynamism to the system? And if we want to give a little dynamism and the goal of the project to minimize the air leakage and maximize the filtrations, therefore the joint pieces are creating another important point. So we work on the direction of origami. And then we say, how about taking it a little bit further? And this time, there can be a system, but it has lots of iterations. And these iterations can respond to environmental benefits. Therefore, we can make these systems as a shading systems if we want to in a building skin, where we can grow the plants, but also we can kind of make these systems respond to the environment, get their natural light, because the lighting is a major concern, even though you're using LED strips in these vegetation systems. And then we are looking for physical components, and we are looking for computer tools. We are fabricating the system again, prototyping starts, and then we started with manually a little bit, how we assembled the system. And then after this manual movements, we connected to the, again, computational systems, which you can see on this side, which is responding to the sun and which is moving on that direction. I'm almost done. And how we can use existing buildings and how we can use the buildings already built. And for example, this is one of the examples of controlled environment and how you can manage your vegetation system grow on that field. And I would like to end this presentation in a way, if we think beyond this urban agriculture and vertical farming, why we cannot find multifunctional systems, and why not vertical farming also clean indoor air, to reduce energy consumption, like improve health and well-being, and also shade the buildings, and why we are not using buildings already exist to grow our vegetation, and instead of creating new farmlands and